At the end of this lecture, you should be able to confidently answer this question. How does the decision threshold you use for your probabilistic classifier affect how well your machine learning model performs? Now, at this point in time, you know that there is a more than one metric that you can use to evaluate your classifier. But then, how would you choose a machine learning model that works well for you? Now, different machine learning models might make sense in different contexts. A model for classifying cancer will be different from a model for labeling cats and dogs. When you're labeling cats and dogs, it's okay to get a few of these wrong. In order to answer this question, we need to go back in time a little bit to a previous section where we considered binary classifiers. We want to classify whales as fish or mammal, and we used a logistic regression classifier for this. This was early on, and you know that logistic regression works off of probabilities. When we try and classify the whale as a fish or a mammal, at the output, we don't get a predicted label. The output gives a probability score. As an example, let's assume that the probability score is expressed in terms of the whale being a fish or any input instance being a fish. And in the case of a whale, this probability score turns out to be 0.45. If you're using logistic regression as our machine learning model, let's plot this problem on a graph. On the y-axis, we have the probability of the animal being fish, and on the x-axis, we have the full range of feature inputs that could go into this classification problem. Now, the curve that we'll get for all possible output probabilities is a sigmoid curve or an S shaped curve, which ranges from 0 at one end, 0 probability that the input instance is a fish, to 1 at the other end, a very high probability that the input instance is a fish. If the features that were input into this machine learning model were things like this particular animal lives on land, breathes with lungs, it does not lay eggs, then the probability of it being fish is very, very low, of the order of, say, 5%. Now, this probability goes up as the features that you specify to your machine learning model changes. Let's say it's between 40 and 60% if you know that the animal lives in water, breathes with lungs, does not lay eggs. The fact that it lives in water increases the probability of the animal being fish. And at the extreme other end of our probability spectrum is the probability of 95% if you pass in a feature set which says the animal lives in the water, breathes with gills, and lays eggs. The probability of this animal being fish is very high indeed. Now, it is this logistic regression curve that we have to use to answer the question: is the whale a fish or a mammal? In order to convert this logistic regression curve of probabilities to an actual predicted label, you need to specify a decision threshold. A decision threshold is basically a line through this probability curve. And if the probability of the input instance being a fish is above the decision threshold, you'll classify that animal as a fish. If the probability is below the decision threshold, you'll classify that animal as a mammal. We've drawn this decision threshold at the halfway mark, the 50% mark. However, these need not always be the case. Where this decision threshold lies depends on many factors, including what problem you're trying to solve, the shape of the curve generated by your logistic regression model, and so on. Once you've chosen your decision threshold, all probability output which lies to one side of your decision threshold will be one predicted label. So if probability is less than p threshold, you'll basically say your input instance is a mammal, because remember, on the y scale you're measuring the probability of the animal being fish. On the other hand, if the output probability of your classifier is above the p threshold, then you'll classify that animal as a fish. If probability greater than p threshold, the input instance is a fish. Basically, in order to build a good classifier, this choice of p threshold becomes extremely important. In order to understand this, let's consider two extreme cases. In the first case, we'll consider a p threshold equal to 1, a very, very high threshold value. We'll use the same example as before, our machine learning model to detect cancer. If our p threshold value is set to 1, our machine learning model becomes an always negative classifier, because it will always say that the person or the medical diagnosis is that there is no cancer. The threshold value is very, very high, none of the probabilities will go beyond the threshold value, our cancer diagnosis will always be negative. The confusion matrix, when you set your threshold value to 1, looks a little different. It looks like what you see on screen. Notice that the predicted label of cancer has 0 instances. Whether cancer was actually present or not, since our machine learning model always says no cancer, there are no instances where cancer was predicted. Now, let's see how this affects the metrics that we use to evaluate this model. For our always negative machine learning model with a very high probability threshold equal to 1, recall is 0%. That means for all instances where cancer was actually present in a patient, our machine learning model got 0 of these correct. On the other hand, precision of this model is infinite. This is because, if you remember, precision is a measure of quality or exactness. Precision is the accuracy of the model when it actually detects cancer. Because this model is always negative, it never detected cancer, which is why the precision becomes infinite. This classifier is way too conservative. It's obviously a very bad classifier. You're not detecting cancer at all, you're always negative. Classifier is too conservative while making cancer no cancer decisions, which is why recall is 0 and precision infinite. If you go back to our S-shaped curve, here this curve now represents precision versus conservativeness. Precision is measured on the y-axis and conservativeness on the x-axis. So if you have a model with very high precision, it means that model is highly conservative. So let's say you start off with high conservative, high precision. As the model becomes less conservative, it becomes less precise. So sometimes you have to give up precision in order to have a more liberal model or a less conservative model so that you actually detect cancer in the cases that it's present. At the other extreme, you could move your decision threshold, the p threshold value, all the way down to 0. When p threshold is equal to 0, your classifier is an always positive classifier, which means it'll detect cancer in all instances. No matter what probability score is output, it'll always detect cancer. The evaluation metrics you'll find now have switched over to the other extreme. Recall here becomes 100% because we always say cancer. All cases of cancer have been correctly detected. Recall is 100%. Precision is much lower though, because we predict cancer when cancer doesn't really exist. Precision is 14 upon 1019, which is 13.7%. A vast majority of people don't have this rare case of cancer, but we've said cancer exists for all of them. That is why our precision is low. A classifier is prone to a different problem. The classifier is not conservative enough. It's too liberal in dispensing cancer diagnosis. It's basically forcing a lot of people to have cancer treatment when they don't really require it. Moving to a graphical representation, you can plot recall versus a conservativeness of a decision threshold. Recall is on the y-axis and the conservativeness of our decision threshold is on the x-axis. We go from 0, where we are not conservative at all, to 1, where we are very conservative. This S-shaped curve looks somewhat like this. Notice that recall is very high, reaching 1 or 100% when our decision threshold is not conservative. When our decision threshold is very liberal to the left of this graph, our recall is very high, and recall steadily falls as you make the decision threshold more conservative. And really, these S shaped curves of precision and recall versus the conservativeness threshold should show you that there is a very clear trade off between precision and recall. A model which has very high precision will have low recall, and a model with low precision will have very high recall. And when you make the decision for what machine learning model you want to use, once you have all of them evaluated, you have to find the right trade off between precision and recall for your problem statement. This trade off lies somewhere along this curve. This curve captures how precision falls as recall increases and recall falls as precision increases. The output of your classifier is typically a probability score. In the case of logistic regression, you get a single probability score, and you have to use a decision threshold to determine what that probability score represents. What is the predicted label of your classifier based on that probability score? Now, this decision threshold determines how conservative how liberal your model is. This decision threshold directly affects the precision and recall values of your machine learning classifier. A very conservative classifier is one whose P threshold is very close to 1, very close to 100%. This will have a very low recall but a very high precision. On the other hand, if your classifier is not conservative enough, where the P threshold is closer to 0, you'll have a very high recall but very low precision.